So here's what's next. We have section 5.3 in your notes. You had all these words. They all pertain to parts of a wave or a function of a wave. You have amplitude, wavelength, frequency, hertz with the cursor that's frozen on the screen there. And then you've got some other things here. The first thing that I want to do is make sure that you understand a couple things about the parts of a wave. So you're going to want to draw yourself a wave. And I told you this was going to be ugly. Oh, that's really ugly, but we're going to work it anyway. I'm better on notebook paper, not so good on a smart pad. How's that for an ugly wave? Draw your own ugly wave. They do look like ugly mountains, but we're going to be okay with that because we're nice and accepting. Okay, this very top part of a wave, you may know what that's called?
Crest.
Very good, I heard it. The crest. I don't have that word up there for you, but it is called the crest. Do you know what the bottom part of a wave is called? Very good. Trough, not troph. Trough, like a water trough. For pigs, cows, whatever. And it's shaped like a trough too, right? Okay. The distance, you can say this a couple different ways, but it's usually said as like the distance between crest to crest or the distance from trough to trough. Somebody said it. What'd you say? Very good. That is the wavelength. Okay? Doesn't matter which. And you can find wavelength other ways than crest to crest and trough to trough. For example, this is kind of the halfway point on the wave, right? So if I'm starting right here, then I need to do like a complete trough, a complete crest. If I go from here to here, this distance would still be the wavelength. As long as I start at the same place and end at the same place on the waves, I do not have to go top to top and bottom to bottom. I could do the wavelength anywhere in between, from here to there, etc. Okay? All right, amplitude. What's that? Yeah, it's how high the wave is. Now, I'm not going to try to draw a line right now. I'm going to do the line this way. If I could put a line about midway down these, I know it's on an incline and I'm sorry, but if I could like put a line like that down the middle of my wave, this line represents what's called the rest position, meaning if the wave didn't move at all, it would just flatline, right? It would go still, like water. You know, you bounce on it on a float or something, it starts to make waves, and then when it stops, it's just a flat line. If you're doing amplitude, you're doing the distance from the crest to the rest or from the trough to the rest. That's amplitude. And the other way to say it is wave height. So that's amplitude, so is that. They should be the same number. Like if this is 2 units tall, then this should be 2 units low. Unless your wave is drawn like mine and then it's not drawn to scale. Okay, anybody know what frequency is? It's kind of how often. It's sort of how often. I'm going to write it right here. Frequency is the number of waves per second. Like how many waves go by every second? The unit of that is either number per second or hertz. Like the rental car place, we abbreviate it capital H, lowercase z. So if you see 4 hertz, what does that mean? 4 waves per second. I'm probably really going to stink at this at the bottom, but we're going to try it anyway. So like if I make myself a section of space and I draw a wave through here, faster is probably better. Let's see how many waves went by. Let's assume that this is 0 and this is 1 second over here at this line. Since it starts kind of at the halfway point, that would be 1 complete wave right there. There would be 2 complete waves, 3 complete waves, 4 complete waves, 5 complete waves. How many hertz is this? 5. You could either say 5 per second, or you could say 5 hertz. Either one of those works, okay? So the bigger this number gets, that means the tinier these waves are going to have to get, right? If I was going to fit 10 of these in there, I'm not sure that I'm capable of doing it, but I can give it a good try. What I'd have to do is fit in one whole wave, like 1, 2, I'm not going to do this well, am I? 3, 4, I don't know. Okay, I stink at drawing waves. Can you see the orange one? Kind of. I was going to try to make it 2 for every one of these, but I kind of ended up stinking at that. What we clearly can say is this: the orange one has a higher frequency than the black wave because there's more of them in the space of a second, right? Okay, one of the main things that I want you guys to understand is this relationship. Basically is this: if frequency goes up, if you increase frequency, you increase energy. That's going to be a big concept for us. If you think about, okay, if you've ever stood in a pool or a pond and you've made waves with a float, have y'all ever done that? Like bounce up and down on it and make it move? If you're going to make lots of waves, you have to put way more energy into it than if you're going to just make a couple of waves, right? It's the same idea here. The higher the frequency, the higher the energy. Think about this. There are some types of waves that have enough energy to kill you. No, not a microwave. Definitely not a microwave. Do you know what would do it? Do what? I don't think I have them on here now. No, y'all are making up stuff now. On the back of your reference table, you have this thing called the electromagnetic spectrum. Gamma rays, okay? Now look, this says absolutely nothing about frequency. You do get this for your final exam, so you know that they want you to be able to use it if it's on there, okay? The relationship that you need to make, too, is that the longer the wavelength is, the lower the frequency. The shorter the wavelength, what? Well, the more energy and the higher what? The higher the frequency. Just like I drew my bad drawings on the screen. Like the higher the frequency, the closer they had to be together. The smaller the wavelengths had to be. These are increasing in energy. I mean, this is not on here. You have to know that in your head. So as you go from radio to gamma, they get increasingly more dangerous. You can see this little portion of the spectrum. It's just this little piece from this dotted line to this dotted line. That's the visible spectrum. That's light. You can't see any of the rest of it. Okay? But radio waves you're surrounded by right this moment. You're surrounded by them all the time. They're not causing you any harm. You're surrounded by microwaves, and you're surrounded by infrared, and you're surrounded by visible light, and there's no danger to that in the sense, you know, that they're not going to kill you or anything. You're bathed in them. Now, when you get up to ultraviolet, we start to get a little dangerous because UV light has the potential to change your DNA. It's used to disinfect. It's what we use to disinfect like goggles, and it's what's used to irradiate food sometimes to make it so that like spinach, like raw produce, if it's been irradiated to get rid of bacteria that might be on the surface of it, they can use that. You're blocked from a lot of the UV light that comes from the sun. Our ozone blocks you primarily from most of the B and all of the C. What do you end up getting? Huh? There's 3 types. Do you know what they are? I heard somebody say vitamin C. That is not UV. There's A, B, and C, you know. So they block most of the dangerous stuff and leave you with a little bit. Are x-rays good? No? No. I mean, they have enough energy that what do they do to your body? Do they go through you? Yeah. UV doesn't go through you. I mean, your skin is able to stop it, right? You get sunburned if you get too much of it. Yeah, that's rough. But x-rays are able to go all the way through your soft tissues. They have more energy. What about gamma rays? Yes. If you get around enough of these from like a nuclear bomb or a nuclear reactor that's melting down, or like cancer radiation, it kills cells in seconds. So, hey, you can pack up in just a second. We got time. So, this is, this is in order of frequency and wavelength and energy, and you need to get those kind of concepts. What we're going to do on Monday with it is we're going to bring this full circle. You remember at the beginning we talked about how Rutherford could not explain why a metal when heated would turn red, orange, yellow, white hot. Okay, we're going to put it all together now. You know all this stuff about electrons and energy levels and sublevels, and now we know some stuff about waves and energy. If we put it all together, we should have an explanation for how it went in that particular color pattern. Or why some flame burns blue or some things are white instead of another color, okay? What's your homework for the weekend? Study. Yep. Study for the test on Tuesday. All right, you can pack your stuff up. Put your chairs up, please.